Yes, thank you very much. It's a pleasure to take over. Next speaker is Simone Gallivanone
Hi
from
everyone.
Milano Bicocca. He will speak on Szegő and Poisson kernels on Grauert tubes and Lie group actions on these tubes.
Today, first of all, I want to thank the organizers for letting me give this talk. And as the title say, I'm going to talk about like equivariant version of the Szegő and Poisson kernel over Grauert tubes boundaries. Briefly, an outline of the talk. I will start by introducing the geometric setting. I will define Grauert tubes, their boundary, and all the geometric properties that I will need later to define the operators. Then I will introduce the operators and state the main results, which is about the scaling asymptotics for these operators. And in the last slides, I will present very shortly a pair of application of these asymptotic expansions. This talk is based on a joint work with Professor Paoletti. Okay, first of all, I want to introduce the Grauert tubes, and I'm going to give two different definitions. The first one goes as follows. The context is always MK, a compact connected d-dimensional real analytic Riemannian manifold. So M and K are both real analytic, and everything basically is real analytic. So geodesics are real analytic, and exponential mapping is real analytic, and so on. It was proved by Brewett and Whitney that in such context there exists a complexification of M in which M embeds as a totally real submanifold, and this complexification is essentially unique, and it comes together with an anti-holomorphic involution which fixes M. It corresponds in some sense to the conjugation. Then it was proved by Guillemin and Stenzel that eventually restricting this complexification, there exists a real analytic non-negative function, which I call ρ, such that the M corresponds to the zero locus of this function. Rho
May I
is
ask,
in,
the complexification is open, is that correct?
yeah, yes. Uh, then ρ is invariant with respect to the anti-holomorphic involution, and ρ is strictly plurisubharmonic. What?
Go ahead. Go
Okay,
ahead.
is strictly plurisubharmonic, which means that if we define omega as in the slide, so I delta bar rho, we get a Keller form on the complexification. Uh, Moreover, it was proved that on the complexification without without m inside, the square root of rho satisfies the Monge-Ampere equation, which is the equation in the slide. So one defines the Grauert tubes of radius tau to be m tau, which is the sublevel with respect to tau square and the function rho, together with the Keller form omega and the complex structure J. This is clearly a strictly pseudo-convex domain inside M tilde. Okay, another definition, which is more, let me say, intuitive, is the following, and it comes from the papers of Lempert and Zook. First of all, let us identify the tangent bundle and cotangent bundle. So the structure that we have on one, we have also on the other one. And we want to define a complex structure over the tangent bundle. And in particular, we want to define the so-called adapted complex structure. How to define that? The point is it is defined by asking that the Riemannian foliation is holomorphic. That is, for every geodesic gamma, the maps psi gamma, as in the slide, from a suitable open strip in C into the tangent bundle is holomorphic. In the map, the dot is just the velocity vector, and NB is the fiber-wise dilation, so the multiplication by B. It was proved by Lempert and Zook that this is enough to define uniquely this complex structure J-ad in a tubular neighborhood of M inside the tangent bundle. Moreover, since we are working in the real analytic context, we can take the exponential mapping and complexify it. And if we take the imaginary time exponential, we get that it relates the square root of rho with the norm function on the tangent bundle. In particular, it was proved that it defines a Kähler biolomorphism within the open Grauert tubes as I defined in the previous slide, and the open Grauert tubes defined as a, let me say, cobalt bundle in the tangent bundle of radius tau together with the canonical true form and the adapted complex structure. Just to bring things down to earth, let us see an example, a very simple one. Let's take the n-dimensional torus. So is Rn over Zn, and the exponential mapping is, one can make computation and see that it's just can be interpreted as the sum of the vectors, where the sum is intended inside the torus, of course. And clearly, its complexification is just Cn over Zn. And again, we can complexify the exponential mapping and we get the complex exponential mapping, which is as in the slide. Basically, we add the imaginary part, always thinking as the sum inside the quotient. And we can take the imaginary time exponential, which is basically taking the exponential where we take only v2 and we call it v. And this is the maps that relates this function square root of rho and define the square with the norm function and define the Kähler biolomorphism. In particular, in this context, if one choose holomorphic coordinates z, one can compute omega and rho very explicitly.
Simone, may I
Yes.
ask you, does the real exponential for real vector v1 and v2 0, does that preserve the level sets of rho?
I see, yes.
I see.
Let's now move for what actually interests us. And it's not the open Grauert tube, but its boundary. Its boundary is an hypersurface inside the complexification, so it has odd real dimension, which is true dimension of m minus 1. And hence it's not a complex manifold, but it has a CR structure and also a contact structure. Let me briefly explain how to define this structure. First of all, we have a contact form, which is given by restricting to x tau to the boundary, the one form defined as the imaginary part of the rho. And if we take the square root of rho and we take the Hamiltonian vector field, of course the Hamiltonian vector field is meant inside the complexification with omega defined before. And it is tangent to x tau, and if we can restrict it to the proper vector field on x tau, which I will denote it with the subscript tau, and we will call its flow the homogeneous geodesic flow. It's like a little bit of abuse of notation, because we said that the square root function is related to the norm function, and the Hamiltonian flow of the norm function is the true homogeneous geodesic flow, but in this context they are related. And one can do some computation and prove that if one defines R tau to be this rescaled version of this restriction of the Hamiltonian vector field, it defines the proper Reb vector field of this contact manifold. Moreover, as I already said, we have a CR structure, that is the tangent bundle decomposes in a part which is complex and a part which is totally real. The maximal complex subbundle is given by the kernel of the contact form, and the real direction is given by the Reb vector field. Together with the CR structure, of course, we have the natural Zygo projector, which I call pi tau. It is, in the sense of Boutet de Monvel and Guillemin, a toy-plate structure associated to the symplectic cone generated by the contact structure. And it will play an important role for us, the operator the square root of rho, which is the Toeplitz operator generated by I multiplied to the Hamiltonian flow of the square root of rho. A few computations shows that it is a positive elliptic self-adjoint Toeplitz operator. Okay. What plays an important role in also in the in my in the just sorry just to point out the fact that the Grauert tubes boundary is a CR manifold and a contact manifold, but it's not Sasaki. It's not Sasaki because one can prove that the homogeneous geodesic flow, and which is basically the flow of the Rep vector field, is not CR holomorphic. So, with respect to the circle bundle context over Keller manifold, here working is a little bit more complicated. Sorry, I'm going back to the slide where I was. Anyway, an important role in our results is played by the choice of local charts. We work with the so-called normal Heisenberg local charts. How to define them? They can be defined through as induced local charts from a proper choice of holomorphic local charts on the complexification. And how we define that? First of all, we fix the center along x tau, we'll call it x, and then we ask that the derivative with respect to z0 is in the complex span of what gives the Rep vector field, in the sense that the vector field R, once restricted to x tau, gives the proper Rep vector field, and the other direction are in the correspondent subbundle with respect to the h tau that I defined along tx tau. Moreover, we ask that the defining function of the boundary, which is rho minus tau square, has an expansion up to the third order, which is properly as in the slide. Once we have all these requests, we have the so-called normal Heisenberg local charts for m tau, and then taking the induced local charts, we get the Heisenberg local charts that we need on x tau. But the point that I want to underline is that using these charts is very common to work in additive notation. So when I will state the results, I will use additive notation. What do I mean by x plus theta v? I mean basically the image through the local chart of theta v, where the local chart is, understand, the one centered at x. And also we can identify a point theta v with an element in the tangent space at x of x tau. So we can basically write x plus a tangent vector. And this still makes sense with this abuse of notation. Okay. Finally, since I need to talk about the equivariant operator, I need to talk about the G action and how it interacts with the space and the operators that I will define. To do so, we will always work under the assumption that G is a compact connected Lie group that acts via isometries on the starting Riemannian manifold. Then one can prove that it leads to an holomorphic and Hamiltonian action on the open Grauert tubes, which preserves the function rho. I will call phi the moment map of this Hamiltonian action. Moreover, clearly, if I have an holomorphic action on the open Grauert tubes, if I restrict it to the boundary, I get a contact and or CR, in particular CR holomorphic action, and then one can prove that it's also a contact action. And it can be also proved that it commutes with the homogeneous geodesic flow. It comes from the fact that the holomorphic action preserves rho, basically. Let us denote G hat the dual of G, so it's the set of equivalence classes of irreducible representations, and so I will denote by nu any irreducible representation, and I will denote by x nu its character, and dim nu the dimension of its representation space. Since the action is via isometry, we have an induced unitary representation of G on L2 of M and the RD space. I haven't said what's the RD space, but the RD space is basically the space of CR homomorphic functions. In general, it is the intersection between L2 and of x tau and the CR homomorphic function, but since we are working in the compact case, this is the space of CR homomorphic function. this unitary representation on this 2RD space commutes with the operator, the Laplacian on L2 of M.
Excuse
Sorry?
me, Simone.
Yeah.
So CR holomorphic functions are complex valued functions.
No.
Real valued.
Yeah.
Satisfying what?
They are restriction of holomorphic function on M tilde. So I take a CR holomorphic function is just a restriction of a holomorphic function on M tau to the boundary.
And why is it real valued?
In fact, in general, they can be complex. In fact, yeah.
Complex valued.
Yeah. Sorry.
Thank you.
Sorry.
Thank
Sorry.
you.
In general, they can be also real, but in general, they are complex. Yeah. And the point is that since the unitary representation commutes with this true operator, we have two things. First of all, we have the eigenspace decomposition of these with respect to these operators of the two Hilbert spaces. And moreover, since we have a unitary representation, we have the Peter-Weyl theorems that gives us an isotypical decomposition. And so the fact that the unitary representation commutes with the operators allow us to say that the isotypical decomposition respects the eigenspaces. So each eigenspace can be decomposed in isotypic components. And finally, I need to make an assumption. All our results are works if we work under this assumption, which is the manifold, the Z tau defined as the zero locus of the moment map intersection with X tau is non-empty, and the action is locally free on Z tau. This may seem quite a restricting hypothesis. Actually, it's not so restricting, and it's necessary to so that the Z tau is a proper submanifold of X tau, and it is also a G invariant and submanifold, and is also invariant with respect to the action of the homogeneous geodesic flow. And a very simple example, I mean, it seems a strict request, but actually one can, if we assume that the action is, for example, say, locally free on the starting manifold MK, then it's also locally free on Z tau. So it's not so restricting. And from this, I'm ready to start introducing the operators. First of all, I will introduce the equivariant Poisson wave kernel. And to do that, let me call mu j to be the eigenvalues of the positive Laplacian. Also in the previous slide, when I was talking about Laplacian, I always mean the positive Laplacian. And the mu j are the mu j square actually are the eigenvalues of the Laplacian. So the mu j are the eigenvalues of the square root of the Laplacian, if one wants to be precise. Then, as I already said, we have a decomposition of L2 of M in eigenspaces. And then we have finally decomposition in isotypic components. So let's denote the Vj nu, the nu isotypic component of the Vj eigenspace. We can choose for each fixed j and nu an orthonormal basis of this space, which is finite dimensional. And it was proved by Boutet de Monvel that there exists a maximal radius such that all the eigenfunction of the Laplacian can be complexified in the open Grauert tubes of radius tau, if tau is less than this maximal radius. And of course, we can then restrict this holomorphic function to CR holomorphic function on X tau, so we get proper CR holomorphic functions. How we define the Poisson wave operator? We define the equivariant Poisson wave operator as the operator who has a kernel that can be written in the form in the slide. Here we have what appears is the Fourier transform of a compactly supported smooth function. we have a tempering factor, the exponential one, which basically is necessary to temper the growth of the eigenfunction, which is known which are known to grow exponentially otherwise. And then we have this sort of projector. This is not a proper spectral decomposition because this last part is not a projection in general. I mean, even if we start from an orthonormal basis, when we take the CR holomorphic functions, we don't get an orthonormal basis of hx tau in general. So we cannot assume that this is a projection, and so this is not a proper spectral projection, but still this kernel makes sense as is well defined. Before getting into the theorem, I need a few more notations. We studied the scaling asymptotics, so we fixed 2 points, x1 and x2 properly. I will explain later how. And we consider shrinking neighborhood around this point and study the asymptotic expansion of the kernel with lambda that goes to infinity. Our scaling term is square root of lambda. Then also, since we have the g action and z tau is g invariant, we have a finer decomposition of the tangent space of x tau in point along z tau, which is of course the span of the Rep vector field. Then there is the tangent space to the orbit, j of the tangent space to the orbit, and a remaining complex subbundle, which I denote th. Finally, I will denote x with the exponent g times chi to be let me say, the orbit of the point x with respect to the g action and the action of the geodesic flow, but we take the action of the geodesic flow restricted for t inside the support of chi. As we will see, all this plays an important role in the next theorem. So let's move into this theorem. First of all, we proved that if x and y don't live in a proper locus, then the kernel is rapidly decreasing in lambda. In particular, where do the 2 points have to live? First of all, x must be in the orbit that I previously defined of y, and also x must be along z tau. These two conditions together actually implies that also y must be in z tau. In fact, we said that z tau is both invariant for the g action and the homogeneous geodesic flow. And then we have the proper asymptotic. So we fix x1 and x2 along z tau. Since the action is locally free, as we assume, there exists a finite number, say rx1 of element in G and an element in the support of chi, which we can suppose unique if we take the support of chi small enough, and such that x1 is in the orbit of x2 with respect to the action of T1 and the GL, basically as in the slide. And then, for a suitable choice of the shifting in theta and v, in particular, we concentrated with various choices of this Vj, but the most general case is very complicated to make computation, and the asymptotic expansion is not intelligible. So I prefer to keep like one of the simplest case in this talk. And so I'm presenting the asymptotic expansion for Vj along j of the tangent space to the orbit in xj, and we assume that theta j and Vj are not very big, but their growth is controlled with lambda and this epsilon prime. Then we proved that for lambda big enough, this kernel decomposes in a sum of Rx1 terms, each one related to the corresponding GL, and each term has a proper asymptotic expansion, which is the one at the bottom of the slide, where we compute very explicitly the principal term. In particular, what's interesting in this, of course, we have the interaction of of chi. We have the part relative to the isotypical component that we choose, and we have a polynomial growth in lambda, with the proper exponent that we computed explicitly, and we also have the growth with respect to the radius of the Grauert tubes. Moreover, we have the kernel is rapidly decreasing with respect to the VJ. And then, oh, sorry, there's a few more terms which I'm not spending much time over, which are the term in S1, the exponential a to the I theta tau, T1, and this F chi nu, which are other correcting terms that comes from the computation, and they are strictly related to the operator. I will spend a few words later on this. So just a brief sketch of the proof. How do we prove this result is the following. First of all, we taking the kind of spectral form of our operator and doing some computation, and also using how the projection into the isotypical components is defined, one can rewrite the kernel as an integral over g times r of this, what you see in the slide. So what appears is the characters of nu, then there is a part which comes from the Fourier transform of chi, and then there's an operator, which I denoted pt plus 2i tau, evaluated not in xy, but shifted in x with respect to the g action. And what is very important for the proof is that this operator, pt plus 2i tau, it was proved by Zeldich that it is a Fourier integral operator of complex phase of degree minus the dimension of m minus 1 over 2. Zeldich proved even more. He proved that modulo smoothing operator, this operator is what he called a dynamical Toeplitz operator. Why he called this a dynamical Toeplitz operator? Because it's very similar to a Toeplitz operator. A Toeplitz operator is the compression of a pseudo-differential operator with respect to the Toeplitz structure, or the Szegő kernel, the Szegő projector, as you prefer to call it. But in this case, we don't have the compression only of a pseudo-differential operator, which is the Q tau, which I then defined in the slide, but we have also the composition with a pullback operator. The pullback is not a pseudo-differential operator, it's a Fourier integral operator. So what we get is not a Toeplitz operator, not in the sense of generalized Toeplitz operator of Butte de Monvel and Guillemin at least. And so they are called dynamical Toeplitz operator. Again, Q is a pseudo-differential operator of the proper order and with a proper symbol that can be computed at least the principal term quite explicitly. And the terms, sorry, which you can see here, which I said that are related to the operator very strictly, comes from the principal symbol of this Q. Sorry, let me go on. What we did next is we put the microlocal expression of the Szegő the Szegő kernel on x tau, which is due to the theory of Butte de Monvel and Jostran, and the principal term is explicitly computed for Grauert tubes in a paper of Paoletti. And we inserted that and used the composition theorem for Fourier integral operator to compute an explicit phase for our equivariant Poisson wave kernel. The phase takes the form in the slide, so we have where x1 and x2 are fixed, all the other variables, we have integral over these variables, and in this phase appears what? The g action, appears the geodesic flow, and the function psi tau, which is the functions the phase function of the Szegő projector, which is related to the defining function of the tube. And then what we did, basically expecting this phase function and doing some work with the integration by parts and restricting properly the integral, one can prove that the first part of the theorem, which allows to restrict actually the total integral defining our operator to shrinking domain with the parameter 1 over square root of lambda. And then, since we are on shrinking domains, we can use normal Heisenberg local charts to parameterize things, and center, of course, in x1 and x2. And then we can expand the phase of the Szego kernel quite explicitly, because, as I said, it's related to the defining function of x tau, which in normal Heisenberg local coordinates have as a proper expansion to the third order. So we could expand that and get an explicit oscillatory integral in all the variables. And the fact that the action is locally free also allows us to split the integral in a sum of integrals on shrinking neighborhoods of proper points in G. And finally, using classical techniques of microlocal analysis, so stationary phase lemma, followed by some computation, allows to get the asymptotic expansion. Okay, let's now move to the other operator, which is quite similar, but instead of starting with the eigenvalues of the Laplacian, we start with the eigenvalues of the Toeplitz operator that I defined at the beginning. We said it's positive, elliptic, and self-adjoint, so we have the discrete spectrum, which is lambda. We can assume lambda 1 less than lambda 2, and so on. And again, we have the composition of each eigenspace inside the Hardy space into isotypical components, and the two decomposition are compatible. And again, we can take this rho j nu k to be an orthonormal basis of each component of each nu isotypical component inside each eigenspace. And what we get is we define the equivariant smoothed Szego kernel to be the kernel of the operator defined in the slide. Again, we have the smoothed part defined by chi, and then we have this time a true projection. So this is a true spectral form of the operator because these rho j are on orthonormal basis. For the rest, the form is quite similar to the other. In fact, what we got is a very similar result. First of all, the kernel is rapidly decreasing on the same locus. So under the same exact hypothesis, we have first a decomposition of the kernel in a sum of terms, and then we have an asymptotic expansion for each term. And what's different from the other one is basically the growth in lambda and tau, which is different because for reason that I will explain in the next slide. And what is different is the part relative to the operator itself, which are the exponential a to the I tilde theta tau and the f tilde. Why these are different? Basically because, again, repeating basically the same argument of the other operator, we can rewrite the kernel as in the slide, so as an integral over g times r, where there appear parts relative to the isotypical components and the Fourier transform of chi, and then an operator, which I denoted u tau square root of rho, shifted with respect to the action, and this operator is explicitly e to the it de rho. So it's a one parameter group of Toeplitz operator. And again, Zeldich proved that this operator, modulo smoothing operators, is a dynamical Toeplitz operators, as in the slide. So what's similar to the other is that is again a dynamical Toeplitz operator with a pullback operator given by the homogeneous geodesic flow, which explains why the results that we got is very similar to the other one. But what's the difference? The difference is on the order of the pseudo-differential operator and its principal symbol. In this case, it's a zeroth order pseudo-differential operator, and also its symbol is different. That's why some terms are different and the growth in lambda and tau is different. But for the rest, the technique applied in the other case also applies in this case, pretty straightforwardly. Finally, I want to move to the application if I have time. Do I? Yes. And the first and most obvious application is Weyl laws. In particular, for the equivariant Szygő kernel, smoothed equivariant Szygő kernel, we could use that to compute a proper Weyl law relative to the dimension of the Knut isotypical component of the eigenspaces. And while for the other operator, we couldn't compute it in strictly a Weyl law. In fact, as I already mentioned, we have that problem that the inner part is not a proper projection. So what we could compute is something that is not a Weyl law, but it still gives some information about the norm, the square norm of the eigenfunction. How we prove this standard technique is basically tracing the operator, so integrating the kernel along the diagonal and then doing some more computation. And what we got is an asymptotic expansion for this Weyl law, again, where we have terms, we have a proper growth, a polynomial growth in lambda, and a controlled growth in tau, which is the radius of the tube, and then we have some constant related to the g action and the isotypical component chosen. Here we had to assume that the action of G is free on Z tau, and the dimension of M is at least 2 times the dimension of G. This is still not particularly restrictive, and why we had to ask that the action is free is basically to do all the computation and gets to this very explicit principal term. Otherwise, the Z tau over G, for example, wouldn't be a smooth manifold, so its volume wouldn't be properly defined. And finally, the last application is relative to the distribution of eigenfunctions, of complexified eigenfunction, of course. And what we got is that we have a pointwise estimate on the absolute value of the eigenfunctions. In particular, to do this, actually, we didn't use exactly the asymptotic expansion that I give, but we also proved that a similar asymptotic expansion holds in unrescaled variables, and we use this unrescaled expansion to give these estimates on the growth of the absolute module of the absolute value of the eigenfunction. Finally, what we also could estimate, basically using the above expansion together with the estimates due to Zeldich on the square norm of eigenfunction of a complexified eigenfunction of the Laplacian, we got an estimate on the equivariant, let me say equivariant because here nu is fixed, Usimi distribution of eigenfunction. And again, what's interesting is in the first, the absolute values grows exponentially, but what we compute, and it is well known, what we compute is quite explicitly, and we have a sharp estimates of the polynomial growth that goes with the exponential one. And of course, when one takes the Usimi distribution, what happens is that the exponential growth is simplifies between the two terms, and so the polynomial growth becomes more relevant. And in fact, the estimate that we have is polynomial in the eigenvalue. With this, I have said everything I have to say. If you thank me for your attention, first of all, and if you give me 1 more minute, I would just want to say a few words about the bibliographic references. First of all, the work of Butte de Monvel and Jostrand about the microlocal description of the Szygő kernel. Then there's the paper Professor Poletti and me, on which the talk is based. Then there's the paper of Butte de Monvel, where he proved the fact that the eigenfunction can be complexified inside the Grauert tubes of a proper radius. And again, the paper that I cited for the principal symbol of the Szygő kernel on Grauert tubes. The paper of Zeldich, where I took the two results from about dynamical Toeplitz operators, and then 2 papers of Cheng and Rabinovitz, where the first they studied the Poisson and wave kernel and the Szygő kernel over Grauert tubes, but in the non-equivariant case. And then three papers, the two from Guillemin and Stenzel, and then the one from Lampert and Zook, where the Grauert tubes are defined and all the geometric properties are discussed. And finally, the last paper from Zeldich is about the estimates on the eigenfunction of the Laplacian, the complexification of the eigenfunction of the Laplacian. With this, I finished. Thank you again for your attention.
Thank you very much for your beautiful talk, Simone.